Hello. We are going to be discussing the relationship between power and sample size in this presentation. This figure here is a power simulation plot that I generated in 2010. And we were trying to working on a study design, and each of the different colored lines here represents a different set of questions that we wanted to ask, a different study design, how it was set up. The sample size is represented on the x-axis, going up to 10,000. Beyond that, we knew we wouldn't have enough money to do that. So then on the y-axis, we have power. So this gives us a nice look at the relationship between power and sample size. Now the red line is not a good option. We don't have power to ask those questions, whereas the green, orange, and black lines are very similar. And so whichever one of those we like best, we could reasonably pick and say we have a good chance of running a successful study and identifying something interesting. This is something that you want to do when you're designing a study, is get an idea for what your expected statistical power is going to be, so that you can have a reasonable chance of being able to get the answers to the questions that you want to ask. So we'll start our discussion out with looking at the difference between population variability and sample variability. So within populations, we have Darwin's finches here on the top left, a family of spiders that are quite different morphologically from each other, maize, different population variability in maize, and human diversity. There's lots of variation in human populations as well. And we have a good feel for this. I think this is very intuitive. Now, sample variability is related to that, but it's a little bit different. Here I have a sample of people. I did a Google image search for smiling person and took the first 10 images that I found on Google that were flagged for reuse. So we have 10 individuals, first 10 pictures I found, nice little sample. This doesn't necessarily completely represent the entire population of the world, but it's a sample. Here we have the next 10 images, another sample. This sample is different from our previous sample. For example, if we were looking at the proportion of females that show up in our sample, we have 80% in this one, where the proportion was smaller in the previous sample. We have a third sample. Again, each of these samples has a slightly different flavor, different characteristics. There's variability between our samples. So if we do the same study over and over again, we're going to get slightly different results. The idea is to take a large enough sample that those results are consistent and similar if we were to rerun studies over and over again. We also want to be sure that the sample we take actually came from our target population. If it comes from some subpopulation and we don't realize that, then we're going to have some biases in our results that might affect the reproducibility of our study. Now, we might want to sample from a subpopulation. We'll talk about that a little bit more later, but that can be one way that is helpful to decrease your sample variability. One example of that would be if you are doing a case control study. Maybe you want to take a group of cases and compare them to some controls from the larger population. And then we want to ask the question, what's different about these cases and these controls? What makes the cases have a higher risk of having the disease or the outcome? And then again, every time we do this over and over again, we're going to get a slightly different sample. And we want it to have a large enough sample size that the differences between samples are small. Now, the relationship between statistical power and sample variability is inverse. So larger sample variability will result in less statistical power. If we want more statistical power, then we need to try and influence that sample variability so that it's smaller. And statistical power is kind of a difficult concept for people at first. I know I found it confusing when I was first exposed to it. This is essentially the probability that a statistical test will reject the null hypothesis when the null hypothesis is true. To think about that a different way, this is a measure of the likelihood that your experiment will be successful if the exposure you're measuring actually causes the outcome. If there is a causal link between the two, what are the chances that you're going to be able to observe that in your study? Let's go ahead and simulate some studies here and look at how that plays out. So we're looking at tumor growth over 3 months, and in the population at large, that is about 1 centimeter normally distributed with 1 standard deviation. In our group of individuals with the XYZ mutation, that growth is actually accelerated to 1.5 centimeters with a 1 centimeter standard deviation over 3 months. And we can make the assumption right now that the frequency of the XYZ gene is about 0.5. So 50% have it, 50% don't. This is pretty optimistic, and we'll look at what changing that frequency does a little bit later. Let's start out with a sample size of 10. So we can expect about 5 of our samples to have the mutation and about 5 of them not to have the mutation. And then over here on the right, we have our first simulated study. Sample 10 people, genotype them, measure them at the beginning, and follow their tumor growth over 3 months and see what happens. Before we look at this further, let's go ahead and pick this figure apart a little bit so we know what we're talking about. On the y-axis, we have the tumor growth. So that's a change from the beginning of the study to 3 months later. We have an XYZ group and an XYZ negative group, those with and without. And then on the right, we have our power. So that's the proportion of all of the studies that we're simulating where we actually saw the difference. We had a statistically significant difference in our sample. And then these violin plots here in the middle, let's look at those a little bit more closely. So again, here we have violin plots, same figure. This is the distribution of tumor growth over our sample. So you can think of this sort of like a histogram, let's say. If we plotted all of our samples where everybody landed along this line, the distribution here, the violin plot, gives us an idea of where they're clustering. It's a pretty normally distributed group here. Lots of them in the center, around 1, not so many further out. Also included in the violin plot is a box plot, so we can see the different quartiles, the interquartile range, where our individuals lie. We also have the median represented by this dot in the middle, and if we have the distribution extending beyond the 4th quartile, we can see where the outliers are. So let's go ahead and go back to our simulated sample. So if we rerun this, so this first sample that we look at, we were not able to see a difference. And if we continue on and we do a bunch of these, it takes us until our 26th try to actually see the difference between these two populations. Now again, we know that there is a difference. The XYZ gene does cause a faster tumor growth over 3 months, but because of our small sample, we can't really differentiate those from each other. Now if we do this a whole bunch of times, say 1,000 times, and we see how often we get a statistically significant result, that's going to be down around 8 to 10%. If you propose this study to a grant committee, they're going to say you only have a 10% chance of successfully identifying this difference. No, we're going to fund somebody else and not you. So you want to know what your power is. You want to show them that you have power to see what you're looking for before you make this proposal. So how can we change that? Let's increase the sample size to 100. That's the only thing we're changing here. We're just changing the sample size. So now we're going to expect about 50 people to have the XYZ mutation and about 50 people not to have the XYZ mutation. And as we go through, we see a much higher proportion, close to 80% of our studies where we are successfully identifying that difference between the two. We have a lot better statistical power for this study design. And our grant committee is much more likely to approve the study and give us funding to try it out. They may ask us to get even a slightly higher sample size to increase that power a little bit, but this is much better than the previous study design. So we'll come back to this difference between population variability and sample variability again. This is really important to understand. So on the left we have population distribution, and we see the XYZ negative group, the XYZ positive group. There is a difference between them, but there's lots of variability in people, and those distributions overlap. If you just looked at one person and said, oh, their tumor growth was 2, you would not be able to definitively say whether they had the XYZ mutation or not based on that information. Now, if we look at our sampling distribution with a sample size of 10, this shows us the change in our sample mean and the variability of our sample mean. So if we run this study over and over and over again, our sample means for the XYZ negative and XYZ positive group will be distributed as shown on the left. Now again, there's a little bit of overlap there, quite a bit, which is why we have a low amount of power. It's difficult statistically to tell those two groups apart. But if we increase our sample size, the distribution of the sample mean is going to change, and we're going to have a much higher likelihood of being able to distinguish those two samples from each other, and thus we will have greater statistical power. Now, I mentioned before that the frequency of the XYZ gene is important. We have equal sample size for each of these because our frequency is 50%. But what if it were smaller? Then that would affect our sample distribution. If the frequency of the XYZ mutation were as low as 10%, then the distribution of the sample mean for the XYZ positive group would be much greater. And then again, you're going to have a lot more overlap between those distributions, and you're going to have much lower statistical power. So let's rerun our study again. Simulations. This time, we are changing the frequency of the XYZ mutation to 10%. So now, in our sample, we're going to expect only 10 XYZ positive individuals and 90 XYZ negative individuals. So when we rerun this, we see that our power has dropped significantly down around 30%. And that's not a good thing. You do want to have an idea for the frequency of the mutation that you're looking for if you're doing a genetic study, or the frequency of the exposure that you're measuring, so that you can have a large enough sample to be able to account for the differences in the two groups. So how do we increase power? The first strategy that we can use is increase the sample size. Everybody, I think, has a good feel for that. Get a bigger sample, your statistics are less variable, and you get better results. We do need to be aware that if our exposure is not common, that just increasing the sample size may not be as helpful as otherwise. If the exposure is similar in both groups, then we have a balanced design, and that's going to affect our power much more strongly than if we have an unbalanced exposure. So if only 10% of people are exposed, then there's going to be a lot more overlap between the distribution of those two samples, and that's not a desirable situation. Now we can just keep increasing the sample size, and that XYZ positive group, the sample size in that group is going to increase as well, just more slowly. If we took 1,000 samples, then those distributions would be much more separated, and it would look a lot better. Even 500 probably would be sufficient. You can also change the study design to change your power. That's something else that we can have control over. If we do a case control study, we can sample that subpopulation of cases, and then from the larger population for controls, we have a balanced design that's going to help us get a little bit more bang for our buck. It's going to cost less, and in some cases it's even impossible, if the disease is rare, to not do a case control study. Now, the drawback is that your sample is taken after the event occurs. So there's a lot of questions you can't really ask in a case control study because it's difficult to measure those things after the event occurred. In a cohort study, where we sample them and then see what happens, we do need a bigger sample size because those disease outcomes might be less frequent in the population. But we can also have a much richer data set and a lot of information that we can gather at the beginning and throughout the course of the study while we are observing whether or not individuals get the disease or have the outcome. Another thing that we can do is a randomized trial. Now in this case, we are not, it's similar to a case control study, but we're not sampling subpopulations. We are changing the frequency of the exposure. We're controlling that. So we give some people the exposure and we don't give other people the exposure. There's less bias here and it's balanced, so we can have a smaller sample size. But some exposures are probably not ethical to give people. We can't tell this group, hey, you're going to smoke, let's see if you get cancer, and this group over here, don't smoke, and we'll see what the difference in cancer rates is. That's not ethical. But for drug design, for testing drugs, this is a great design because you can look at the effect that a drug has on your population. And it's a really nice design if you can use it. Another strategy we can take to increase power is to make fewer comparisons. So we have our throat cancer example here again, but this time our change is that there is no effect of the XYZ mutation on tumor growth over 3 months. So if we look at this, we run 16 simulated studies, and on the 16th one, we see a difference. This would be a false positive finding, which is not desirable, and these happen. And so we need to plan for them happening. If we do this for a long time, we can see that these happen about 5% of the time. That's because our p-value that we're using is 0.05. Now, if we are asking one question, we're making one comparison, then we can expect about 5% of the time that we will have a false positive result come out of our data if there's not really a difference between them. What happens if we ask 2 questions or 3 or 4? Then the family-wise type 1 error, or the probability of getting a false positive in any of our comparisons, if we just take a p-value cutoff of 0.05, increases rather rapidly. And so if we ask more questions, we make more comparisons down here along the x-axis. As we do that, our type 1 error rate increases to where when we get up to 100 comparisons, we have almost a guarantee that at least one of those is going to show up as statistically significant, even if all of them are not at all related. You can make up random data, and if you do this long enough, you go up for a fishing expedition, you're going to find something that looks statistically significant even though it's not. Now, this obviously is not desirable. So what we have to do when we make multiple comparisons is we have to change our p-value cutoff, maybe with the Bonferroni correction or something like that. the effect that this has is that our power decreases. So as we make these additional comparisons, as we account for the additional comparisons, the probability of finding what we're actually looking for or finding that true positive decreases dramatically to where at 100 comparisons with our sample size of 100 people, we have no real expectation of being able to identify anything interesting that's biologically relevant. Just to make that point a little more clear, this group here has published some interesting spurious correlations. Here we have U.S. spending on science, space, and technology happens to be highly correlated with suicides by hanging, strangulation, and suffocation between the years of 1999 and 2009. Do we believe that? Obviously, no. That's not a valid, there's no biological relationship there. What they did is they went and looked at a whole bunch of different health outcomes, and eventually they found one that happened to randomly correlate with STEM spending in the US. Likewise, per capita cheese consumption correlates with the number of people who have died by becoming tangled in their bed sheets. I like this one. This is great. So if you don't want to become tangled in your bed sheets and die from it, eat less cheese, right? No. There's no true causal relationship between cheese consumption and dying from becoming tangled in your bed sheets. But again, if you go on a fishing expedition and you just keep looking for something, eventually, because of just random dumb luck, you will find something that is statistically correlated, even though there is no causal relationship between the two. Here's another example. This is a very short clip from a Dude Perfect video, and they like to do trick shots and stuff. They're kind of fun to watch. My son especially enjoys them. So here we have a front flip off a trampoline, throwing the basketball across the field and making a basket. Now this is fun to watch. We kind of had this intuitive understanding that they probably did that shot about, I don't know, hundreds of times maybe, before they actually made the basket. And that's fine, and it's fun to watch, and it brings a smile to our face, but similar results in research are less obvious. If we go on a fishing expedition and we find something after looking at 100 different compounds and we say, ooh, this one looks interesting, and we only publish that one result without telling everyone that we have looked at 100 others, that's misleading, and we need to be clear about what we've actually done so that people have the whole picture. Because I don't believe that that guy could do another front flip and make a basket on the first try. If we publish results without giving the full picture, we're going to be publishing studies that are not reproducible. And so we need to be careful about that. Now, one other way that we can reduce sample variability and increase power is if we sample a subpopulation that is more homogeneous. So a more homogeneous population will result in less sample variability and thus higher power. And as long as we are aware that we are sampling that subpopulation, this can be a great tool for us. If we want to look at cancer rates of a specific type of cancer in Caucasian children, then that might give us a better chance of finding cases, but again, that may not exactly be applicable to an African American population, those results. As long as we're aware of that, this can be a nice tool. So just to recap, different strategies for changing power, for increasing our power, or changing our sample size would be the first one. We can take a bigger sample and get more power, but it can also cost us a lot more. In some cases, it can be impractical because we've sampled all of the cases that we know about in the area, and we can't increase the sample size. So then maybe you want to try a different strategy, or maybe you just can't afford to increase your sample size. You can choose a study design that increases your power. You have a case control study that will balance your case control ratio. But again, the disadvantage is that you're sampling after the event. A cohort study can be really nice. You have a much richer data set, but it's going to cost more because you need a larger sample to be able to have the same amount of power that you would with a case control study. Statistical power, that is. For a randomized trial, this is really nice because you can condition out bias. It's a nice balanced design, has a lot of great properties, except you can't always randomly assign exposures to people. Certain exposures are not ethical to purposely expose people to. And there's lots of other study designs that you can explore as well. You can, often one of the easiest ways to change power is to change the number of comparisons that you're making. Sometimes people will approach me with a data set and they'll say, here's my data set and here's all the questions I want to ask. And I have to tell them, you need to ask fewer questions or you're not going to be able to find any answers to any of your questions. So pick the questions that you really want to ask and we'll start with those. Now obviously we are scientists, we want to ask lots of questions, and so that can be painful sometimes not to be able to ask all the questions we want. But that's sometimes the choice that we're left with. And lastly, if we modify the variability of our population by sampling a subpopulation that is more homogeneous, then we will have greater power and be able to have a smaller sample size if that's an issue. Of course, we will have less ability to extrapolate. We will not be able to apply our results possibly to other unrelated subpopulations or to the larger population in general. But this can be a really good strategy in a lot of cases. I hope you've enjoyed this discussion about power, sample size, and variability. Thanks for watching.